All right, let's go ahead and do part 2 of section 5.3. I just went ahead and got the bagels I had baking out of the oven, and we're back here in my garage. Just want to give you another example of induction before we move on to strong induction in section 5.4, which is just a little bit, it seems a little bit more advanced than, or rather a little bit more powerful than ordinary or weak induction, but it's not really. We're not going to get into the details, but it's another proof technique very similar to induction. Well, like I said, let's go ahead and do one more example, this one dealing with divisibility. So it turns out there are a lot of patterns with regard to the way that numbers interact with each other. Prime numbers that are not prime, or therefore composite. Divisibility properties, the way that various numbers interact with one another, is actually the basis for a lot of really advanced mathematics and a number of applications, including RSA cryptography and other crypto systems that keep information secure in our modern age. We're not going to get into the details of some of that, but if that's something you're interested in pursuing, the branch of mathematics called number theory is what looks at all these different interactions between the whole numbers. So divisibility, prime numbers, distribution of primes, and that kind of thing. So we're going to talk about this particular claim. So here is, actually let's couch this kind of like we did with the last one, where I wrote down a sequence of numbers. Each term in the sequence had the form of a sum. Let's look at this as another sequence of numbers and see if we can see a pattern in the way that they react to a specific other number. So I'm going to look at, for various values of n, we're going to look at a specific sequence of numbers, namely 3 raised to the 2 times n minus 1. And I think we can start with n equals 0 here. So at n equals 0, 2, and I think my limit to do this mental math is probably going to be reached by the time we get to n equals 3, but we'll see, maybe even before that, we'll see. When n equals 0, what number does this formula give us? We have 3 raised to the 2 times 0 minus 1. 3 to the 0, any number to the 0 is 1. Minus 1 gives us 0. When n equals 1, we get 3 raised to the 2 times 1, or 2, minus 1, which gives us 8. When n equals 2, we get 3 to the 2 times 2 is 3 to the 4th. And already we're taxing my limits here. 3 to the 4th is 9 squared, which is 81, minus 1 is 80. And let's see if we can do this next one. 3 to the 2 times 3 is 3 to the 6, minus 1. 3 to the 4th is 81. 3 to the 5th is 243. And that makes 729 minus 1 is 3 to the 6th minus 1. Now the first ones are pretty obvious. 0 is 8 times 0. 8 is 8 times 1. 80 is 8 times 10. The last one takes a little bit of work, but it's not too bad. We see that 8 goes into 72 9 times, and therefore 720 90 times, and then we have an extra 8. So this last number is actually 8 times 91. Whatever number goes there is not so important, just that it's an integer. Each of these can be expressed as 8 times an integer, which seems to suggest that if we look at an arbitrary term in this sequence, 3 to the 2n minus 1, so far the pattern we're seeing, with a little bit of educated guessing on my part, was that each of these numbers is divisible by 8. In other words, we seem to want to make a claim along the lines of, for all n greater than or equal to 0, 8 divides 3 to the 2n minus 1. Remember, the notation we introduced for this divisibility is this pipe symbol, is how you make it in LaTeX. It's this vertical line that is read 8 divides 3 to the 2n minus 1. Another way of saying that is 3 to the 2n minus 1 is divisible by 8. So let's see if we can prove that claim by induction. Again, never a bad idea to remind your audience, your reader, whoever it is you're talking to, that you'll be doing a proof of a certain type by way of contradiction, a contrapositive, by induction in this case. As before, we will deal with the base case. By the way, I encourage you, when we're doing these examples, I encourage you, if you'd like, and if you feel comfortable doing so, pause the video and see if you can do the next step of the proof before I do it, and then start the video up again and see if we're kind of on the same page. Now the base case, in this case, notice we started with n equals 0. We didn't start at n equals 1. So when n equals 0, we've already done the computation. 3 to the 2 times 0 minus 1 is 0, which we already noticed is 8 times 0. So the base case holds. Because being able to write 3 to the 2 times 0 minus 1 as 8 times something, some integer, means that 8 divides that value. So now the inductive hypothesis, assume for some fixed k that 8 divides 3 to the 2k minus 1. And what this means, in other words, that means 3 to the 2k minus 1 happens to equal 8 times m, say, for some integer m. That's all that means, just by definition of divisibility. We're going to use that fact in a moment because, remember, just like in the first part of this, part of section 5.3, and in previous examples we've done of induction, we always want to use the inductive hypothesis to prove the inductive step. If you ever do an inductive proof and it turns out you're not using the inductive hypothesis, you want to go back and make sure that you're really doing the proof properly, because generally the inductive hypothesis will appear somewhere in the inductive step. Otherwise, what that's a sign of is otherwise maybe you're just doing a direct proof and you don't even need to do induction. So sometimes you have a valid proof, it's just being made more complicated than it has to be. So let's look at the inductive step here. And again, feel free to pause the video and see if you can fill in the next step in this proof before I do it. So the inductive step is going to be to show we must prove that 8 divides 3 to the 2 times quantity k plus 1 minus 1. That's what we have to prove now, replacing our k with k plus 1. And it's going to involve just a little bit of algebra, not a whole lot. But what we want to do is somehow use the fact that 3 to the 2k minus 1 is 8 times something in our proof. I'm going to start with this number that we're most interested in and just do a little bit of algebra to rearrange to see if I can get this in there somehow. So let's start out. I want to be cognizant of how visible this is. Let's just start out with this value that we're keenly interested in, namely 3 to the 2k plus 1 minus 1. Now, if I, first thing I really want to do is distribute that exponent, right? We don't want to look at 2 times quantity k plus 1. So I'll distribute the exponent, get 3 to the 2k plus 2. And now, because of this plus 2, what this is really saying is we'll take 3 times itself 2k times itself 2 more times. And all that's saying really is take 3 times 3, or 9, and multiply that by 3 to the 2k minus 1. Now, it's really tempting at this point to say, hey look, we've got 8m right there. And we'd be done because it's 9 times 8m, but notice the order of operations means that we do this product first and then subtract. In other words, this isn't exactly like 9 times this whole thing. We only have 9 times that first part, not times the minus 1. So what I'm going to do is just almost artificially I'm going to get 3 to the 2k minus 1 in there. And the way I'm doing that is I'm adding 1 and subtracting 1 right away from this quantity that's multiplied by 9. Does that make sense? So now, because notice what I've done here is I've really just added 0 in a clever way. That's a trick that's pretty common in math, to get things like this out of things that look like this. make sure you're understanding why we can't just jump right to this formula here. Again, the 9 is only being multiplied by the 3 to the 2k, not by the minus 1. So you can't just jump to this and say 9 times 8 times n. But in a moment, we're going to do a distribution here that allows us to do just that. I'm going to go ahead and erase. Give ourselves a little bit more room to finish this problem off. In the meantime, I'm going to try to figure out a way to clean this more effectively and efficiently between video recordings. All right, let's go ahead and work in that space there. Just picking up from this last computation, put it right there. So I'll copy it up here just to make sure we don't make any mistakes. So far that's what we've got. Now I'm just going to do a little bit of distribution. I'm going to multiply that 9 through this term a little bit. I'm not breaking the whole thing up because that would defeat my purpose. My purpose was to get 3 to the 2k minus 1 in there somehow. So I'm not breaking this sum up completely. I'm not distributing that 9 completely, just between this term and that term. That's the plus 1. 9 times plus 1 becomes just 9 times 1. But now, we do have a replacement we can make. 3 to the 2k minus 1 is just 8m. So let's just replace 3 to the 2k minus 1 by 8m up here. And sometimes what I like to do if I'm doing this computation on the board is I like to write a little ind type above the equal sign right there as a reminder or as a signal to the reader that that's where we're using the inductive hypothesis. We're using the fact that we already know that formula to get our next one. And now we've got a little bit of algebra here. Plus 9 minus 1 is plus 8. And I think you can see how to finish this off. We've got an 8 buried in this term, and we've got an 8 buried in this term. Let's just factor those 8's out. And we get this. Now we're at a point where we know closure of the integers under simple operations means that if m is an integer, so is 9m, and so is 9m plus 1. And so this quantity here lives in the integers, and we have managed to express 3 to the 2k plus 1 quantity minus 1 as 8 times some integer. So we're done. That was our inductive step. From there, we conclude inductively, since we established a base case, since we were able, using the inductive hypothesis, to prove the inductive step, we were able to show that this will hold true for any value n, any value bigger than or equal to 0. In fact, we actually discovered a pattern. Remember I said that those numbers didn't really matter so much, and they don't, as long as all we're trying to do is prove divisibility. 8 times whatever doesn't really matter as long as that whatever is an integer. But now we have a pattern. We can actually see from our proof how those numbers change. I erased it unfortunately, but I think the numbers were 0, 1, 10, 91. Those are not random numbers. If you start with 0, this formula here tells you the next one is going to be 9 times 0 plus 1, or 1. The one after that is going to be 9 times 1 plus 1, which is 10. The one after that is going to be 9 times 10 plus 1, which is 91. And the next one after that would be 9 times 91, which would be 800, oh goodness, 819, I think, plus 1 would be 820. So the next number you should get, if you went ahead and did 3 to the 8th minus 1, would be 8 times 820. So we do see this proof not only showed what we wanted to, but it also gave us something extra, a little bit of constructiveness to it. So that's kind of another bonus of inductive proofs, is sometimes they will give you even more insight into the original pattern you're trying to prove in the first place. So I'm going to go ahead and give myself just a little more room here because I want to write down a problem for you to work on at home. And again, feel free to check in some virtual office hours with me or make an appointment with me to talk about this. Check in with each other. Try to meet up with each other over Hangouts or with Stephen, who is still available as a supplemental instructor for this course. and see what you can do to get some progress on this problem. Again, I'm not going to have a quiz on this section, but we do have problem sets. Problem sets 5.1, 5.2, and 5.3 are due uploaded by LaTeX PDFs to Moodle by April 3rd, I believe is the due date. Double check that on Moodle. I think that's the due date I put for 5.1, 5.2, and 5.3. And don't forget that you are being asked to present 2 problem solutions to me by video. You can put them in the same video if you haven't done either of them yet. If you've already done one, you only owe me one, and you're off the hook. I think only 1 or 2 of you are off the hook at this point, though, if you've done both of them already. So here's a problem for you to continue to work on induction with. It's similar to one we did in class actually before spring break, before COVID-19 hit us all and threw us all for a loop. Go ahead and use induction to prove that n squared is strictly less than 2 to the n for n greater than or equal to 5. So notice implicit in this is a base case. It seems that we're being told the base case will probably be n equals 5, so that's where you want to start. There was a really good question I received by email yesterday, and that's, well, what if it's not true for a particular case? Like if the textbook were to give you a problem where the claim doesn't appear to be true for a particular value. Well, it could be that you're just making a mistake. Just double check and make sure it really does fail. It could also be that you're using the wrong base case. For instance, if we started with n equals 4 in this case, we would have 16 and 2 to the 4th, 16 over here as well. 16 is not strictly less than 16. It's less than or equal to. So this isn't true when n equals 4, which is probably why this example starts at 5. So again, thank you for your time. Thank you for being with me. And let's see some work. Let's see some questions. Anything we've talked about today, any of the problems, anything that pops up, just shoot me an email. And as usual, I'm here for you. I'm here to support you in whatever way possible, even beyond the scope of our class. So I hope to hear from you soon, and I'll talk to you later.